we are ready to go. Slide set up from the current slide. Sorry we're late getting started. The last announcements I wanted to make, I think I told you when the second mini term started, which was basically last week, that my office hours were adjusted some because I was here till 4:45 every day, Monday through Thursday before, and then Birmingham campus Friday, 7:45 to 11:45. But second mini term started, and that means my classes go until 8 o'clock on Tuesday, Thursday, which means I have to shorten my office hours on Monday, Wednesday, basically till right after this class is over with, 2 o'clock. Well, I don't leave at 2 o'clock normally on Mondays and Wednesdays. I'm usually here closer to 4:45, sometimes even 5:15. But today, not. Even though my office hours officially end at 2, normally I am here later. Today, I will need to leave between 2 and 2:30 because we've got a meeting on the Birmingham campus at 3. So I will be leaving between 2 and 2:30 to get there at 3 o'clock. So today's up? No. Officially, they're not my office hours, but times when I'm usually in my office, I won't be. I'll be over there. Now, I'll probably leave there before 4:45 too, because I forgot and brought something here that I was supposed to have left at home, and so I've got to get home and get it to the person who needs it before, while I can still get it to her. Okay? So, strange today. Friday, in fact, the next 2 Fridays. Normally I'm on Birmingham campus 7:45 to 11:45, but not the next 2 Fridays. I've got a new treatment where they're starting on this Friday, and because it's a new treatment, they're giving me a low dose this Friday and a full dose next Friday. The low dose is 300 milligrams, which isn't very much, you know, not much at all. Over 7 hours, okay? They really are trying to do it slowly. Now, if everything works well and I don't have any reactions, they may speed that up a little bit. But then next Friday, they give me the full dose, which is 1,000 milligrams, which is 1 gram. I mean, that's not a lot, except it's spread over 7 hours.
And it's diluted.
Huh?
It's diluted in saline.
Oh, definitely, yeah. Well, actually, they start off with giving me 2 Tylenol to keep me from having fever, because sometimes that will happen with this drug. They give me a Benadryl to knock down an histamine reaction because people have gone into anaphylactic type situations. And they give me a steroid to suppress my immune system. So they do all that and let that take effect before they ever start the drug. Now, all the steroid is given IV, the others are given by mouth. So I'm sitting around waiting until they're ready to do. And then they start it, and they drip it very slowly in saline or whatever they have to do it in. And they say, plan to be there 7 hours. Now, again, I'm hoping it'll go well, no problems. They'll probably speed it up. But I won't be on campus because I start at 7:30 in the morning, and it'll be way past 11:45 before they're through, my guess. Okay, and even if not, I'm going home and going to bed because the Benadryl knocks me out, you know. So I'll try to get work done as much as I can until the Benadryl takes effect, and then I'll shut it down. Okay. Good deal. Any questions? So that's the changes to office hours this week and next week. All right. Last time we would introduce the concept of curvature. We had introduced the concept of a unit tangent vector. All right. Now, if this is your curve, the blue line here is your curve, the unit tangent vector is always tangent to the curve at the point where it's measured from. Okay? Now, notice here when the curve is bending very slowly, the unit tangent vector is changing very little. But as the curve changes more drastically, then, and forgot to do this, so you can see it better. as a curve curves faster, this is a pretty slow curve, that's a pretty rapid curve, where it's curving faster, the unit tangent vector is changing quite rapidly. So the curvature is large where the unit tangent vector changes directions rapidly. Now remember, it's a unit tangent vector, meaning all these lengths are unit length, one length, okay? So the unit tangent vector varies in direction, but not in length, and the greater the curvature, the greater the change in unit tangent vector. Now that should lead to a concept here that the magnitude of the change of the unit tangent vector is somehow a measure of the curvature. And the next formula, definition, whatever you want to call it here, says exactly that. Okay? Let R of S be an arc length parameterization. Okay, now remember what that is? That is a very handy thing to do all our referencing to, but it's usually a very hard thing to determine analytically, what the R of S. But it's the arc length parameterization. And capital T, of course, is your arc length parameterization. That's a vector quantity, that's your displacement vector, as a function of the arc length. So that's a parameterization of the displacement vector. Capital T is the unit tangent vector. The curvature at this point R of S is the quantity denoted by lowercase Greek letter kappa. Looks like our capital kappa, and the capital kappa is just a bigger form of that. But that's the Greek letter lowercase kappa as a function of S, which remember is handy for equations, but not very handy to do in reality, is equal to the magnitude of the time rate of change of that unit tangent vector with respect to S. Okay? So if you can get an R of S, which sometimes you can't, then you take a derivative of that. Let's go back a few slides. And, well, this would work for any parameter, but R prime of S divided by magnitude of R prime of S, that's your unit tangent vector. Okay? So take the derivative of your R of S, if you are given that, if you know that, and then divide by the magnitude of RS, that gives you your unit tangent vector as a function of S. Then take the derivative of that with respect to X. The magnitude of that is your kappa, your curvature, as a function of the arc length parameter, of the arc length, S. Okay? Handy dandy, neat little formula, but not very useful most of the time. I think the first example shows one that we can use it, I think. Let's see. I don't think we have a slide for it. Let me see. I think the thing is... well, where is example figure 5? Yeah, that's example 2. So let's do example 1. Pretty simple example here. Compute the curvature at each point on the line R of T. Let me get my pen in black. R of T. Notice this is not an arc length parameterization. This is a regular parameterization. R of T is equal to, now this is a vector, yeah, x0, y0, z0. Okay. I'm out there. This is in 3 space, of course, obviously. And this gives us a starting point for the line that we're dealing with. Okay? Origin somewhere here, starting point here. So x0, y0, z0. Okay? Some point here. That's the initial point of this vector we're dealing with. Okay? R of t. It's just a point on it. Okay? This vector points from the origin to that, the x0, y0, z0. But this is just a starting point for that vector r of t. And then we're going to add to that, this is how we do lines, plus your parameter t times a vector u. Okay? Except, I thought it was going to be the case, but I didn't read far enough ahead. Reading the next little clause or phrase there, where u, the magnitude of u, is equal to 1. What does that tell you? It is a vector for sure. Unit vector. Oh, I thought you said u is a vector. Okay. It's the unit vector. Exactly. So I like to put the hat on the unit vector to remind myself and you and everybody else that is indeed not just any old vector, but a unit vector u.
Just in case you forgets.
What's that?
Just in case you
forgets. Right. That's what it is. It needs a hat on. Okay. All right. So that means, give me some unit vector. Doesn't matter where it's going, right? Some unit vector anywhere, okay? The x0, y0, z0 gets you up to this point, and then you have a unit vector pointing in some direction from that point, and this line then is t, that's your parameterization, times that u. That t could be negative, positive, you know, whatever the u is, that gives you the direction, that gives you the point, and the t gives you basically kind of like a magnitude, whatever that t is allowed to be. Infinity is the line infinitely long, right? So that is a line in 3 space that's parallel to that unit vector u. Okay. So we want to compute the curvature at each point on that line. Ah, a new Cal 3 student. Okay. Oh, no? Okay.
Let's see if you had those tests from yesterday.
Okay.
You had the schedule mixed up.
Okay.
For your schedule.
All right. I don't have a blank one up here. I'll need to run down to my office and get it.
I don't
Okay.
want to interrupt.
All right,
I'll come back.
Y'all, they'll throw things at me, but I'll do it anyway. I mean, they hate to be interrupted. All right. So here is our vector parameterization of a line. It says compute the curvature. How do we do that? I just hit it. But nothing happened, huh?
I think it's turning on.
Yeah, it is.
It's just being slow.
Very slow. It could be that, yeah, it's come on now, that it hadn't cooled down from the previous time and had to finish cooling down before it was going to turn back on. So how do we calculate the
Take a wild guess.
curvature?
Derivative.
Take a derivative. Good start. R prime of t is equal to, what does that first thing give us? No, that's just a point. Zero. Yeah, nothing. Okay? Derivative of this with respect to t, this, by the way, is, in fact, that might be helpful if I write it rather than prime notation, write it in, what's his name, Leibniz notation, dr of t dt. There's no t dependence on that first part, so that's 0. And what do you have? U. Okay, yeah, but take derivative with respect to t, and you just get the u vector, that unit vector. Okay? And what do we do next?
Well, let's see.
Oops. Okay. You got it? Okay. Went too far. Let's go back here. Oops, went too wrong direction. Okay, here's what your curvature, that's what we're looking for is. We need a tangent vector before we can take a derivative of unit tangent vector. So how do we get unit tangent vector? This is how we get it. We got the r prime. Now we got to get magnitude of r prime. Anyone want to make a guess of what that is? 1, because it's a unit vector. So there, all right, yes, exactly. There is Nigel. He was waiting for that to come in. Okay. So that is our derivative of the r prime vector is, of the r vector is that unit vector u. Okay? That's it. That is it. Okay? Now, what do we do with that? Oh, and by the way, that's that. Now we divide that by 1, and this is our unit tangent vector, because that's the direction the vector's going, right? The line's going, and it's a unit vector. So that is a unit tangent vector. Okay? And then what does it say to do here? The kappa as a function of, let's do it as a function of t. If we need to, we'll get to s. That would be then what? Time rate of change of the dt. Now that's not precisely true, but how is that unit tangent vector changing with time? Here's the line. There's the unit tangent vector, unit tangent vector, unit tangent vector, unit tangent vector. It's the same. Not changing magnitude, of course, it's constant, 1. Not changing direction, so its change is 0. Even if that formula isn't right, the change is 0. Well, guess what? The curvature of compute the curvature at each point on a line r of t equal to that. The title of the problem says, a line has no has a 0 curvature. So that is the answer, 0. Okay. All right. And they do give you kappa there as a function of t, just like I did. Okay, and that is 0. Now, example 2.
Which is also.
Okay, that's this one. Okay. The curvature of a circle of radius r. Compute the curvature of a circle of radius r. There's your circle of radius r. I'll blow it up to begin with, just so you see what it looks like up close and personal. Okay. This is a circle, radius r, centered at the origin, and they're giving it as a function of theta. Okay. Why not? That's the easiest thing. That's the polar coordinates are really the easier one to do circles in. Not bad in rectangular, but this is pretty easy. That circle as a radius, as a function of the angle theta, is the vector r cosine theta, r sine theta. That's the unit circle multiplied by r. That expands it from 1 to r, or reduces it from 1 to r, depending on what size r is. But that's your circle as a function of theta. Okay? So there's your r of t. R of theta, sorry. Now, of course, I have to... Okay. Shrink this to get it to write. And it's ready to write. Okay. So your... Goodness gracious, it won't write. There we go. Okay. R of theta, that just happens to be the parameter we choose to have here, is equal to r times the vector cosine theta sine theta. And what, by the way, this is in the plane in R2. R2. You know, XY plane, okay? The vector, without that magnitude of r, that would be the unit circle. With the magnitude of r, it gives it circle of radius r. Okay, what might be our first step to determine its curvature? Take a derivative, dr, this time of theta, d theta, okay, is equal to what? R stays there. This will become negative sine theta, comma, cosine theta. Okay, got it. Next thing we need is the magnitude of that derivative. Anyone want to make a guess what that would be? Or let's calculate it, huh? I don't think so. If that was a unit circle, possibly. Okay, well, what would be this magnitude? The magnitude of this, now, I keep going backward in the book, but it's really, if you go to the top of the page, it's easier, backward in the slide set, easier at the top of the page. That unit tangent vector is r prime that we just did as a function of theta divided by the magnitude of r prime. So that's what we do next. The magnitude of this, I'll write it on a separate line, the magnitude of r prime as a function of theta is equal to what? It's going to be a square root. R squared for sure. Times, actually, yeah. Okay, negative sine theta squared, which would be, so yeah, that would be sine squared theta plus cosine squared theta, which is 1. So it's the square root of r squared, which is r. Okay, there's the magnitude. So here's the vector divided by its magnitude. Hear the sound effects there? And this gives you your unit tangent vector. Minus sine theta cosine theta, if I could write. Okay? And sure enough, that's a unit vector. Test it and see. Square root of sine squared plus cosine. Yeah, that's 1. Okay? Now, what do we need to do to get the curvature as a function of theta? This is as a function of theta. Formula right there. K, this time it's of theta, is equal to, first thing we've got to do is take a derivative of that unit tangent vector with respect to theta, and that would be negative cosine theta, negative sine theta. Very good. Okay? And what's the magnitude of that? 1. Okay? So the magnitude of that would be the magnitude of this thing, which is 1. Okay. Ain't working out right. Oh, yuck. We can't do it that way. Sorry, I forgot. We've got to get it to unit tangent vector. To the arc length parameter. Sorry, I forgot that. It would have been okay, or they said it was okay before to do it in terms of t, but it's not okay to do it in terms of theta. We have to get it to the s function. Okay, so what that means is, and now we have to go back to that one, which was arc length and speed. Your s, sorry, forget this, sorry, we went on a good goose chase, but it wasn't profitable. Okay. All that is true so far, but not useful. And maybe that too, but I'm going to stop erasing because I don't need any more space. I don't think of that. Okay, here's what our S is, but we need this now S as a function of theta, not S as a function of t. This is the bottom of page 706. That's equal to the integral from we'll do a to theta, because we want it in terms of theta, the magnitude of r prime of, and here's just a dummy variable u du, okay? We can use the one we got there. So we do need this thing, and that is r, okay? So our arc length as a function of theta would then be this derivative here is r, right? So that would be r times the integral from a to theta of du. What would that be? R times, yeah, actually theta minus a, but, you know, r theta will suffice for us, okay? Well, actually, let's see. Yeah, yeah, it not going to matter any. So, actually, you can choose the a to be 0. That's what they did. So, and that makes it even easier. Okay. Theta minus 0 times r, so that's r theta. That is your arc length parameterization of this, of this. Now, since that's your arc length parameterization, what we need to do now is back up and do, I did erase too much, didn't I? Our unit tangent vector as a function of theta was equal to, wasn't that just,
Unless you wanted the derivative of it.
okay, yeah, wait. Yeah, that would have given us, okay. I guess here's what we need to do before we go there is, well, from here, we've got s as a function of theta. What we need to do is get, and we got r as a function of theta, so what we need to do is get theta as a function of s. Now remember, capital R is a constant. Little r is your vector. So this basically tells us that theta is equal to s over r, right? Variable theta, this is variable s, divide both sides by r, if I could divide, and that would be theta as a function of s now is s over r. Okay. Now, that's what we want to plug in here. Okay. Let's erase this for now because that's not quite where we want to go. We had to do that to get our r prime, and we did it. Okay, now we go back up here and want r in terms of s, not in terms of theta. So r in terms of theta is this, r, they call it r1 in terms of s over r. Wait. This would, let's see. These little, okay. What you want, and remember this was the bugaboo before, r1 as a function of s is equal to r as a function of s over r, because s over r is theta, and that would be that. So that basically indicates it's a composite function of, well, I mean, it's just like I said here. Okay, let's leave it go like that. And that's equal to, and we come up here, and that would be r cosine S over R, comma, sine S over R, because your theta is S over R. Oops, 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 oops. That's a vector angle bracket. Okay. We've just rewritten this from theta to S. Okay? Now, that's what we take a derivative of. dr1 as a function of S with respect to S. So take it here, and that would be R times what? Derivative of this R with respect to S. Okay, that would be a negative sine S over R times a 1 over R, isn't it? Because you got
Because it'd be S times 1 over R.
right, exactly. And 1 over R is your coefficient. Right. Okay, and this would be comma cosine S over R times 1 over R. Okay. Now, you can factor out the 1 over R's. Okay, that's your R1 of S. Your dr ds, where do they show that? Oh, there it is, yeah, okay. And that merely gets us down to, because your 1 over R, that cancels all those out, and this is your dr ds is then negative sine S over R, comma, cosine S over R, which is basically, if you go back and check it, that's what we said derivative was anyway, minus sine theta, comma, cosine theta, which is exactly the same as what we had before I erased it. Okay? That's your derivative of your R of S, your function as a function of S, arc length parameter, rather than the other. Okay. Now, what was your D? Okay. And that, by the way, was also all right, too many moving parts here. I think we're through.
I have a question.
Yeah.
The R1 of S.
Yeah.
How did you get that to equal R of S over R? Because I know we set S of theta equal to where to go.
Yeah, right here. Theta is equal to S over R.
Yeah.
Okay.
That's theta, not S.
Okay. Now, your R of theta, we had this at the beginning. You're happy with that, right? Okay. Now, and we had to do the dr to get this thing, okay? And we did it, we got it, and we got S as a function of theta is R theta, okay? But we wanted theta as a function of S, so we divide everything by R, and that gives us theta as S over R. So that's why we needed this one, so we could get this. So now we go back to our original one, and instead of theta, we put S over R, okay?
Okay.
Now, and this is your R of S over R. This is that one, and it's R times cosine of S over R, theta, comma, sine S over R, which is theta, okay?
All right, I got that.
Okay, now this is your R1 then. Now we're taking the R1 ds, okay? Why are we doing that? Because that is your unit tangent vector. Nope. Well, it will be. If we go back to, it can be either ds, dt ds, or, okay. Well, okay. phrased another way, well, to get your unit tangent vector that way, okay? So dr1 ds, you're now taking derivative with respect to s of this thing. Okay, now is that what you're asking about? Okay, the r is out front, okay? It's just a constant.
The coefficients.
Right, the coefficient of it, you might say, okay? And then the derivative of this is, with respect to s, is, like you said, minus sine s over r, chain rule times 1 over r. Now that's inside here, but it's still a constant. Comma, and the derivative of this is cosine s over r, and then the derivative of the chain rule of that again is 1 over r. Well, now these are constants, 1 over r. Pull those out, and it cancels out or divides away this r. So you're left with sine of s over r, minus sine of s over r, comma, cosine s over r. So that's our dr1 ds. Okay? Now, now, your unit tangent vector is derivative of that with, okay. And this is also, oops, I've got my eraser going here. Okay. This is also, just like it was before with the unit, this is your unit tangent vector. Because obviously it's a tangent vector with respect to s, and that has unit magnitude. Because you take the magnitude of that, that would be sine squared s over r plus cosine squared s over r, and that's 1. So that is your unit tangent vector. Just as a function of s now, not as a function of theta or anything else. This is your unit tangent vector as a function of s. Okay? That's what dr ds gives you. Well, divided by magnitude of r. And the magnitude of that is 1, so that is your unit tangent vector. Now, we take the first derivative of that, and that's why I was starting to erase at the bottom. Is it all right to do it? Because we've already used this stuff, right? So let's get that out of there, just because we don't need it anymore, mostly because of that. I think we can get rid of that arrow too. Now, what we want to do, kappa as a function of s is equal to the magnitude of dt ds. That's our definition for curvature. Okay? So what we need to do is do dt ds. Well, here we have t, so dt ds would be what? We almost did this before, but we just had it in terms of theta. Say again? Negative cosine. A 1 over r. S over r, right?
S over r.
Right, comma. 1 over r. Negative sine. S over r. Okay? Now what we need to do now is take the magnitude of that. And what will that be? And that will be our kappa. So what's the magnitude of that? The square root of? Yeah. But you're going to square it. So you lose the minus. So you get cosine squared s over r squared, because you're squaring it, right? Squaring that part too. That's okay. Plus, the minus will disappear here too. Sine squared s over r squared, right? But the numerator's there, same denominator. Combine the numerator, and you get 1 over r squared. Square root of that would be 1 over r. So there is the kappa. Kappa as a function of s, which really isn't a function of s anymore because all your s dependence goes away, is 1 over r. So what is that saying? The curvature of any circle any circle is 1 over the radius of the circle. So a big circle is going to have a very small curvature. Also, big radius, small curvature. Small radius, big curvature. It's curving big time here. Whereas a huge circle, it's almost a straight line as its tangent. I mean, well, its tangent is a straight line, but that almost follows.
It doesn't change.
It doesn't change much at all. You got it. So the curvature is 1 over the radius. Okay? That's what we were trying to show. Curvature of a circle of radius r is 1 over r. Done. Okay. Now, here is what I've been trying to say. In practice, this is the paragraph just about the middle of page 713. In practice, it is often impossible not to mark Ashley present. Okay. Got it. Okay. Now, that gives us 2, 3, 6 out of 9. Way to go. We're only missing Tony, Tyrone, Javon. Who's the other? Oh, and Jonathan. That's it. Okay. Okay. Now, I don't think. Okay. Not quite ready for that yet. Okay, in practice, it is often impossible to find an arc length parameterization explicitly. We've done it on these because, yeah, they were pretty simple things. Most of the time, it's not. Fortunately, we can compute curvature using any regular parameterization R of t. Okay, that's what I tried to do before, but we'll be able to do it now. Okay, since arc length S is a function of time t, the derivative of your unit tangent vector with respect to t, let's get me some clean writing space here. Okay. What's that?
Said you might even have a slide.
No, I tried. It wasn't. It'll come up in a minute, though. Okay, I think. Okay. Since the arc length S is a function of time, S is some function of time, S is arc length, T is time, or some other parameter. The derivatives of T, which is what we're interested in, the derivative of your unit tangent vector T with respect to T, with respect to little t, that one t is a 2 and the other t is a t, and S, with respect to T and S, they're related by the chain rule. So here's what we're doing. The derivative of the unit tangent vector as a function of t is written in what's his name notation? Leibniz notation is dt by dt. Okay. Capital T unit vector on top, little t time on the bottom. Well, what is that? Okay. That is dt ds dt. Okay. It's basically chain rule. Well, what in the world is ds dt? Hint. S is arc length. Derivative of length with respect to time is? Derivative of distance with respect to time? Yeah, it's speed. Yeah. They use the V, but it's the italic V, which means speed. This is your speed. The reason they don't use S, they've already used S for arc length. So this is your speed as a function of time times the t with respect to S. Okay? Now, turning that around, then, well, guess what? Guess what dt ds is? Or at least its magnitude.
Probably one.
No, dt ds. Look on the opposite page. Definition for curvature. Okay? So if you did the let's see, how far back do they go? Yeah. All right. And one more thing before we get off of this. The SDT is also, because that's the speed, that's r prime of t, the magnitude of r prime of t. Okay? That's the speed of s. It's also ds dt. There is the little connection there. So if you take the magnitude of this in the front, and this is just a scalar quantity, magnitude of that, what we have then is the magnitude of the unit tangent vector, the first derivative of the unit tangent vector as a function of time, is equal to your speed as a function of time times your curvature as a function also. And I put too many parentheses in there. Okay. As a function of time. Okay? So, your magnitude of your unit tangent vector is speed times curvature. Okay? Magnitude of the first derivative of the unit tangent vector. Magnitude of the unit tangent vector is 1. The magnitude of the first derivative of the unit tangent vector is your speed times your curvature. So, really slow curvature, very small k, at a small speed, is going to have a very small change of rate of your unit vector. The direction is going to change very little, okay? If you got a very large rate of speed with a small curvature, you're going to change it faster because you're going faster, okay? But if you're got a small speed but a great curvature, that's also going to increase your rate of changing your, and certainly if you have a large speed along a very small curvature, you go with a very large change of rate of your unit tangent vector. So, about a dozen ways to look at that. So what you can do with this then, another definition for you, your kappa as a function of time now is the first derivative of your unit tangent vector as a function of time, magnitude of that divided by your speed. And if you didn't want to call it v of t, you could call it this up here, magnitude of first derivative of your unit tangent vector as a function of time divided by the magnitude of your speed, which is r prime of t. Okay, so there's a couple of ways you can express it there. And that shows up, here's the first way.
What a slide.
What's that?
I said, what a slide.
Yeah, I know. Little bitty print. Great big white space. Okay. So this is the one we just had down. The first derivative of the unit tangent vector. In fact, how fast is the unit tangent vector changing? Not with direction, but only magnitude. The magnitude of the change is dependent on the speed and kappa. Then solving that for kappa, I think. They skipped the next step, sorry. It's in your, we did it, but they did, well, I don't know. Let's see if it's on the next slide. No, it isn't. The one that should have preceded this one was what I just had, that kappa of t is equal to, I don't know why they write it this way, but I'm going to write it this way, the way I did. The magnitude of the first derivative of your tangent vector, unit tangent vector, over v of t, which, by the way, is magnitude of r prime of t. Okay. Now, that looks pretty useful, or at least a lot more useful, okay? But Theorem 1 gives you yet another formula. Formula for curvature, if r of t now is a regular parameterization, just how it varies with time, okay? Not an arc length parameterization, but a regular parameterization. Then the curvature, and I think I will blow this up. Let's see. Include both of them in it. Okay? Then the curvature r of t at r of t. Okay. I really don't like the way they phrase that. The curvature at r of t. It should be at some t value, t0 or whatever. Anyway, the curvature as a function of t, okay, is r prime of t cross r double prime of t. Now that hasn't entered the picture at all yet. So that's an easy thing to calculate. Divided by r prime of t, which is basically the magnitude of r prime of t is what your v of t is, but now we're cubing it, not just. So that one was pulled out of somewhere. We won't say where. It may have been a smelly place. But anyway, that's another expression. Yeah, out of your ear. Yeah, okay. Now, how did they jump to that? They're not telling you, but I mean, I think the next.
I think they proved it.
Huh?
Did they prove it? Okay.
Yeah, they do a proof here to get there, but it's they just pulled it right here. Why didn't they lead up to it rather than say it and then have to go back and prove it later? Okay. Now, I guess we ought to do that since they did it. And it does look like it would make sense. All right. So, let's see. I guess we'll use that I wrote before. Okay. Now, well, maybe not. Here's where we're starting. We're starting with some vector r of t. Now, we don't have to write it down, but that's going to be some x of t, y of t, z of t, right? Okay. Now, they don't do that, so I won't either, but we ought to. Then we need an r prime of t, which is going to be whatever those first derivatives are. Okay. Now,
That's your speed.
that's your speed. Now, actually, they're backing up one more step. Okay. Okay. Just as a reminder, the magnitude of r prime of t is equal to v of t. Okay. We said that before, but I had erased it. Okay. Now, if we take that and fiddle around with it a little bit, okay, as in, yeah, your unit tangent vector, t of t is equal to r prime of t over the magnitude of r prime of t, right? Now, expanding that, you get r prime of t is equal to this is your v of t times your t of t. Okay? That's where they're starting. Okay? Now, how did you get there? This is equal to that. This is equal to that. Multiply this side by this, but only doing that, and that gives you this. Okay. Now, that gives you your first derivative with respect to t, all in terms of t. Okay? Now, and v is a scalar function, by the way. T is capital T is a vector function, obviously. Okay. So let's do r double prime of t. Good old product rule. Okay? Now we're going to need this, but it's in the way, but let's do it. What would that be? You tell me. It's v prime of t times t of t plus v of t, I keep writing those v's, t prime of t. Okay, got it. Okay. Now, what we're going to do is take our r prime of t and cross it with the r double prime of t. Okay? So that's going to be v of t, t of t, unit tangent vector, that's r prime, cross with this thing, the prime of t, t of t, plus v of t, t prime of t. Okay. We're going to cross those two vectors. Okay. This is kind of like a distributive law, but you're crossing everywhere. Don't change the order. Okay? So what would that be? That would be a v of t, v prime of t, t of t cross t of t, plus v of t, t of t, cross v of t, t prime of t. Okay? Now, I've sort of rearranged some of the order there. The point is, what is a vector crossed with itself? Crossed with itself. Zero. Remember, crossing, you get mutually perpendicular. Dot product, you would, that gives you the magnitude squared. But the cross product, a vector cross with itself is zero. Remember, right-hand rule, if it crosses with cross, it doesn't cross at all. Okay?
I hear your crosses in two different places.
Well, I know, I said I wrote them in different places. It really doesn't matter. The scalars can go anywhere. And those are scalar functions. But this part, the point is that's zero. That's why I wrote it together to indicate this is zero. Okay? This is not just zero, it's a zero vector. Okay? All right. But who cares? It's still zero. Okay. So then we have v, and let's take this up to here, and this would be v of t squared times t of t crossed with t prime of t. Okay. Now, and by the way, that shows up on this page. Okay. I'll blow it up for now, but we'll write on it in a minute. Okay. That's what we just did. This cross product is 0. This cross product is the only one that matters. It's v of t squared times unit tangent vector times the derivative of unit tangent vector with respect to t. Okay. All right. That's equation 4 at the bottom of the page. Now, the unit tangent vector and the derivative of the unit tangent vector, they say note this, they're all orthogonal. Okay? I can't recall that we actually proved that, but we're going to take their word for it. They are. I know they are. Okay? So if they are, that produces some vector that is perpendicular to both of them. Okay? And see, first marginal note, it's over on the side here. And I think that we did prove that way back then. We did it with a dot product and showed they were orthogonal. So if you go back and review that, it was example 7 in section 13.2. We did show those were perpendicular to each other, orthogonal. Okay. Now, which, by the way, if they are orthogonal to each other, and I'm going to have to shrink this down to do it, since these things are orthogonal, t of t is perpendicular to t prime of t. Okay? The definition for a cross product, remember there's a couple of them, but one involves a sign. Okay? And that says that cross product is equal to, so I'm actually going to, okay, we got their perpendicular to each other. So now let's talk about what it means to do the cross product of the two. That's equal to the magnitude of t times the magnitude of t prime of t times the sine of 90 degrees, which is pi halves. But what's the sine of pi halves? 1, okay? So that means these things are this. Well, what is the magnitude of the unit tangent vector? 1, okay? So that means this thing just comes out being the magnitude of it is the magnitude of t prime, okay? Magnitude of t prime, okay? So that's what the magnitude of this is, okay? Now, this direction is somewhere perpendicular to both of them. So what do we have then? Plugging back into here, this cross product, at least the magnitude of that cross product, let me see which equation 4 is. Yeah, that's it. Let's go back to the very beginning. My nose itches like crazy. Remember what we started with? That kappa of t is supposed to equal the magnitude of r prime of t crossed r double prime of t, the magnitude of that cross product divided by the magnitude of r prime of t cubed. Okay? Now, where we started off, we crossed those two vectors. That's where we did it, right there. But we really weren't interested in the cross product. We're interested in the magnitude of the cross product. Well, what's the magnitude then of this cross product? It would be this v squared of t. I don't like the way they write that. Times just this part here, because this is 1 and that's 1. So this numerator here is simply v of, I like to write it v squared of t times the magnitude of t prime of t. Okay? That's what that cross product is, the magnitude of that cross product. Okay? Now, is that where we want to go with it? I think so. Yeah. Now, the other thing that we need to note, and this is just all over the board here, let me point you back to, I've already pointed back to it once today, and now I can't see it again. It's somewhere back here. Why am I not seeing it? Well, we've already done it, and I hate not to do it again. But remember what r prime of t, the magnitude of r prime of t. Remember what that was? This is indeed v of t. Right? Okay. If you remember that. Now, so basically this is saying this is v of t cubed. Well, here we have a v of t squared. There we have v of t cubed. So knock 2 of them out of there. And now this is telling you the kappa as a function of time is equal to the unit tangent vector prime of time divided by v of t. Or, in other words, this gets right back around to the magnitude of this of t is equal to kappa of t v of t. It feels like we've run in circles here. Okay? But all that manipulation really does show us that this formula does account for kappa of t, okay? Because they all work out coming back to the same value. Okay. Let's actually do something with it. That's enough of that, I feel like. Let's do an actual example. And I don't think we have a figure for this. Maybe we do. It's figure 6. Okay. We're going to use that, but let's not mess with it yet. Calculate the curvature kappa of t, okay, of the twisted cubic r of t is equal to the vector t squared, t cubed. Okay, that's the twisted cubic. And then it says plot a graph of kappa of t. So we compute kappa of t, then plot a graph of kappa of t, and determine where the curvature is the largest. Okay? So how are we going to begin? Now our last formula gave us that kappa of t is equal to, remember what it was? magnitude of r prime of t cross r double prime of t divided by r prime of t magnitude of that cube. Fairly simple formula. So guess what the first thing we're going to need to do? Find the derivative. Always a good answer. R prime of t is equal to, what would that vector be? 1 comma 2t comma 3t squared. Close it. Okay? Second derivative. Does that sound like made to order? R double prime of t is 0, 2, 6t. Got it. Those are both vectors. What's the next thing we got to do? Remember? Look at your formula. Cross them. No, we got to cross them first, then take the magnitude. Oh, we need the magnitude of r prime. We do. We could do that if you want to. You want to do that? Let's do that. Magnitude of r prime of t, since we got it there, we could have done that before we took the double prime, but that's fine. What would that be? The square root of 1 comma, no, 1 plus 4t squared plus to the 4th. Got it. Okay? We'll just leave that alone for now. That's the magnitude of that. Of r prime. Yeah. Okay. It's not squared, is it? No. Okay, that's it. What's that?
We'll have to cube it later on.
We will. We'll cube that later. Okay? In whatever order. If you want to cube it now, we could. And it's a pretty simple thing to cube. You just square that. That gives you 1 plus 4t squared plus 9t to the 4th times, I'm sorry, put an angle, yuck, dumb, times the square root of 1 plus 4t squared plus 9t to the 4th. Okay? Or you could put that to the 3 halves by having, however you want to write it. Okay? This takes more writing, but okay. Done. Next.
We want to
Cross those two. So how do we cross those two? I, J, K. Y'all like doing it this way? Probably not. Remember what we do? 1, 2t, 3t squared, 0, 2, 6t, and then I know you like doing this. IJ 1, 0, 2t, 2. Okay? You love it, right?
Yeah.
All right. Let's do the cross this way. That will be a 12t squared. Okay. And when we cross this way, that will be a minus 6t squared, right? And that will be your I value. Right? Okay. The j's will be 0 that way, but a minus 6t this way. Minus 6tj. Buy that? What's that?
Was there a different way to do this?
Yeah, and this comes out being 6t squared I minus 6tj, right? And then the k. That would be 2k minus 0. So plus 2k. All right. So the cross product there is 6t squared I minus 6tj plus 2k. Right? Now, we want the magnitude of that. And what would that be? Okay, what would that be? Right? No, you don't. Take those out, yeah. Right. Mm-hmm. Right? Okay. Now what might we do with that? Second, take out a 4. So that would be a 2, square root of 4 is 2, and that would leave us a 9t fourth plus 9t squared plus 1. Okay? Now, we need to do that as our numerator, and this other thing we've got there is our denominator. Oh, what a joy. Okay. So your kappa as a function of time, t, is going to be 2 times onto the square root of 9t to the fourth plus 9t squared plus 1 over 1 plus 4t squared plus 9t to the fourth onto the square root of, I'm going to rearrange the order there, 9t fourth plus 4t squared plus 1. Okay. What's that? Yeah, they look awfully close, but no cigars. Okay. Now let's see, where are we? That was example 3. Oh, they left the 4 in there. Or the 2 inside. Yeah, and they left it as the 3 has power. So why they put a radical in the numerator and a fractional exponent in the denominator, I don't know. It looks like what they did was just take this that we had here, and they left it as a radical, but why not put it as a 36t fourth plus 36t squared plus 4 to the 1/2 power divided by 4 was 9t fourth plus 4t squared plus 1 to the 3/2 power. To me, that would have made more sense.
But they're both equivalent.
They are, yeah, it's exactly the same. And what I had was equivalent. Yeah, I just pulled out what I could, but it doesn't matter. Now, that's your kappa of t. This is where you need your computer algebra system or good fancy graphing calculator to plot that one. And supposedly you get, if it's all right, I'm going to erase the part I need to here, and that's this part right here. I think we already have dealt with that, taken care of it. Hopefully we don't need it again. Please don't need it again. And this is the graph they say. If you got a graphing device that will do it, you can check them out and see if indeed that's what it comes out being. Y as a function of, Y is the curvature as a function of time, t. And sure enough, you can't have t's that are positive or negative because all your square roots are always positive. Okay? And it's symmetric about the y-axis. There it is. Now, that's not a graph of the twisted curvature. I mean, the twisted cubic. It is a graph of the curvature of the twisted cube for different t's. And certainly as t's go to infinity, your curvature is going to 0, meaning this twisted cubic is approaching the straight line because t goes to positive infinity or negative infinity. Where is its greatest curvature?
Is it 0?
At x equals 0. Okay? And then it falls off pretty sharply between -1 and 1 in both directions, and then is approaching 0 from there on out. Okay. This is what that twisted cubic looks like when you graph it. And why they have the caption in one place and the graph in the other. This is a fantastically logical. I can't get them both in there, so I'm just going to do it this way. Okay. There's your twisted cubic. Okay. T is -1, it's down here, and from there it goes on almost a straight line this way. T equals +1 here, and it goes almost approaching a straight line that way. Greatest cubic, greatest curvature at T is equal to 0. Okay? All right. And the caption for that is over here. I don't know why they did it this way. The graph of the twisted cubic, that colored by curvature. And what they mean there is your greatest curvature is in the blue part, and you're approaching 0 curvature for the green part. And it keeps on trucking. All right. What a fun problem. Now, they did their cross product similar to what we did, but they just used the one thing. I expanded it and made it, to me, easier to deal with. All right, in the second paragraph of this section, how are we doing on time? I know we just lost one, but we still got a little bit of time. It's what, 7? Okay. In the second paragraph of this section, which is way back at the beginning, it says in chapter 4 we use a blah, 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 blah. Okay? We pointed out that the curvature of a graph, did you finish?
Well, I left it all in blank, but I think
Are you going to come back and try to fill those out?
I can go and grade it, I guess. I don't think it'll hurt too bad. I'm hoping not.
Okay, well, I'm going to grade what you've done so far, but you want to come back before I put the final grade.
Yes, sir. I guess so.
Huh?
Yes, sir.
Okay, all right. Well, I'll grade, but I just won't put it on Blackboard till you tell me to.
Okay. That'd be
Okay.
great.
All right. Have a good weekend.
You too.
Okay. We pointed out that the curvature of a graph y is equal to f of x must involve more than just the value of the second derivative f double prime. We now show that the curvature can be expressed in terms of both f double prime and f prime, which we talked about some at the beginning, and here is that theorem which shows it to us. Okay? All right. The curvature of a graph in a plane, and this is in a plane now. This doesn't apply for free space. Don't even try it. This is in a plane where you can do first and second derivatives, just like they are. The curvature at a point x f of x, xy, f of x, on the graph of y is equal to f of x is equal to, now this is just in the plane, magnitude of f double prime, so there's that dependence on the second derivative, but it's divided by 1 plus f prime of x squared. Now, I like to put that squared over there with the prime, f prime squared of x. They like to write f prime of x squared, which to me could be confusing and you think you're squaring the x. You're not. That's the other. You're squaring the first derivative. And that's to the 3 halves power. Okay? Now, it, in a strange way, sort of resembles what we had before. Not quite. Before we had in free space or any kind of space, you have the magnitude of the cross product of r prime, or you think l prime here, but r prime and r double prime. So a little bit. And down here you had something to the 3 halves power, but down here it was just r prime. So here you're missing the R prime. Here you're adding a 1 plus R prime. So it is different, but a little bit. So here's a conceptual insight. Curvature for plane curves has a geometric interpretation in terms of the angle of inclination. Okay, and that's what this is showing without too much description. Okay. As the angle theta between the tangent vector and the horizontal in this figure, the angle theta changes as the curve bends, and we can show that the curvature, sorry, I can't breathe, curvature K is the rate of change of theta as you walk along the curve at unit speed, and that's what exercise 69 is going to be talking about. So as you're going along the curve here, now what they don't show is that definition when theta is back this way, but either it would be a negative theta or theta along like this. But on the positive side, you know, when you're on this side, here your angle theta, there's your unit tangent vector, okay, at that point. Here is at that point. So you see your theta is increasing. So when you talk about the rate of change of your unit tangent vector, you can do it in terms of the rate of change of that angle theta. And that's what we're talking about here in a pretty broad sense. Do we have time for example 4?
3 minutes.
Huh?
3 minutes.
3 minutes? This is pretty quick. Let's do example 4. Okay? I think we can. Let's see if we can. See, is that figure 9? Yeah, I think we might use this. Compute the curvature of f of x equal x cubed minus 3x squared plus 4 at 4, forgot we had to do it 4 points. X equals 0, 1, 2, and 3. Okay? What are we going to need to do that? First derivative, what would that be? 3x squared minus 6x, and we'll need the second derivative. 6x minus 6. Got it. Now what was that formature? What was the formula for the curvature that we just did? That's abbreviated as formature, by the way. Your kappa of x, this is of functions in 2 space, okay, and that's what we're dealing with here, x, y space, is equal to the magnitude, it's absolute value of functions, not magnitudes. I think I was calling magnitude. It is a magnitude, but to keep from confusing it with a vector. The absolute value of your f double prime of x. I did it again. I'm so used to doing a double. Okay, just do a single. Okay. Divided by 1 plus f prime of x, and it's f prime of x squared, f prime squared of x, and that's to the 3 has power. Okay? So no, I don't think we're going to have time to do it, are we? It's not for 4 points. But we could, I mean, let's get started on it anyway. So, let's plug in first kappa of 0. That should be fairly easy. Your f double prime at 0 is, f double prime of 0 is negative 6, but we're doing the absolute value of it, so that's going to be 6. Over 1 plus, now you got to do f prime of 0. Well, guess what f prime of 0 is? 0. At 0 it is. So that's 1 to the 3 has power, so that's 6. That wasn't too bad. Okay? Let's do the kappa at 1. F double prime at 1 would be 0. We've done that one too, right? Not too bad. How about kappa at 2? Say again? 6 in the numerator. Okay. Say again? Okay. Yeah, I'm looking at that. No, wait. F prime. Okay. F prime would be. Oh, F prime would be 0, wouldn't it? So 1 plus and 0 squared is 0. There'd be a 1 in the denominator. So sure enough, that's just going to be 6 again. So kappa. Is that right? Okay. All right. Sorry. You're plugging. Okay. I guess I didn't understand. Put a 2 in here and you get 6 here, right? Okay. Then put a 2 in there and you get a. Did I hear y'all say 0? That's 3 times 4 is 12 minus 12, right? That's a 0. So that's squared, that's a 0, plus 1 is 1, so that's just going to be 6 also. Right? Okay. This is F prime squared, right? Is that what you're talking about? Or where?
Like 3x squared. Is that 3x squared that F prime is out?
Oh, up here. Minus 3x squared? Is that what you're talking about? Right here. Yeah, that's 3x squared. That's the first derivative, and this is 6x. Is that what you're talking about? Is that right? Okay. So kappa of 2 is also 6. This is going faster than I thought. Kappa of 3, what would that be? I think this is the bugaboo, isn't it? Your numerator would be Numerator would be 12, okay? Your denominator, your first derivative would be, goodness gracious, 27 minus 18, is that right? Is that 9? Okay, so that would, oops. Okay, that's 9. Squared would be 81. 1 plus that would be 82, if I did it right. And then you do that to the 3 power. Boo hiss. Okay, that's a miserable one. I knew we were going to get to that in a second here. It's 12 over 82 to the 3 power, and you can figure out what that is. They say it's 0.016 approximately. Okay, here's the graph showing the curvature at those various points. Okay, curvature kappa at 0 was 6, at 1 was 0, at 2 was 6, and at 3 it's very small but not 0. Okay, and then they show, oh, and here's a function that they graph in there too. All right, good deal. All right, oh, let me give you a few homework exercises here. I don't want you to get away without that. You need something to do this weekend, right? Yes. Do any of the odds 1 through 5, either 6, 7, or 9, or both. Either 11 or 13, or both. 13 or 17, or both. 19, any of the odds 19 through 27. 29 or 31, or both. 33, 35, any of the odds 33 through, goodness gracious, 39, either 41 or 43. Do 45. Stop there. No, wait. Stop. Ooh, wait. I did too many. Stop at 33. I think that's as far as we got. Stop at 33. And where did we end? We finished example 4, getting ready to start the normal vector, if anything's normal. Okay. Good deal. Let's end this.